Hi, I'm David at soldersmell.com, and today I'd like to present you my static test controller. So I'm into amateur experimental rocketry, and this is basically a board that's going to help us characterize our fuel and motors we make, and give us a lot of data on what's going on within the motors. So let me try to explain how a static test works. So basically we've got a motor with a motor chamber, we've got a nozzle which basically is a restriction in the flow of gases from the motor, and we've got an expansion area. Inside of the motor is a propellant. It's usually a solid block of some sort of chemicals mixed. It's got a geometry. I'll draw a cylindrical opening here. When this block of fuel starts to burn, it creates a lot of hot gases which vent through the nozzle outward, creating force. The opposite reaction basically is thrust. This thrust is depending on a lot of factors within the motor. Obviously, if we run a test blind, you'll see a lot of white smoke coming out of the nozzle, and that's it. You don't have a lot of data. So you want to measure some of the properties of the motor. One of the main properties we're looking for is the thrust of the motor, because this is what ultimately is going to propel the rocket skyward. But in order to be able to control the explosion in the motor chamber and keep it at bay, make sure that the motor actually doesn't explode, but that the gases can still vent, is the pressure inside of this motor. Now this we can measure as well. If we make a tap here in the motor casing, we take a piece of tubing and we put a pressure transducer. The pressure transducer basically has a membrane which will deflect if the pressure goes up or down, and we can measure it electronically through current that comes out of this pressure transducer. There's a few types of pressure transducers, but that's basically the general idea. Now what's also important is when you're going to characterize a new fuel in a motor is to know the fuel's burn rate. Burn rate is a really important property of a fuel because it's got a bit of a nasty way of working. If I draw it out on a graph, basically if this is the pressure a propellant burns at, and this is the burn rate of the propellant, basically the millimeters a second that the fuel burns away, it's got a tendency, the higher the pressure gets, the faster the burn rate goes. So it's got a bit of an exponential graph. Now you can see where this is heading. If you start at a low pressure and your fuel burns, it'll increase the pressure in the motor if the nozzle isn't big enough to vent the gases. So basically, if you don't have an equilibrium in your motor, then this reaction is going to be running away, and somewhere at a certain point you're going to have a big boom and you have an explosion of your motor. So it's important to know exactly what the burn rate of the fuel at the different pressures you're going to run at is. Now, the burn rate of a fuel at different pressures is not an easy thing to measure. You've got something like called the Crawford strand burner, which is basically a pressure vessel in which you put a certain pressure and then you burn fuel in it, and you measure how fast it burns. There's another way of measuring burn rate, which is in a ballistic evaluation motor. So basically it's a motor with a really simple fuel grain geometry, like a straight end burner. If you know the size of the nozzle and the size of the fuel surface that's burning, you can calculate how fast the fuel is burning. Now, what our rocketry group is going to try to do is we're building a ballistic evaluation motor, but with a bit of a twist. So basically, your standard ballistic evaluation motor is just a pressure chamber, a motor chamber, with a really simple nozzle being just a hole. you've got a fuel block. Let me pick a different color here. You've got a fuel block, which is basically just a cylindrical block inside of the motor, which can only burn on this surface. So this surface area is well known. The size of the hole, the surface area there, is well known, so you can do the math and calculate it. Now what we're going to do is actually in the fuel grain through the motor casing we're going to embed brake wires, which is just a fine strand of copper wire. The nice thing about it, as the fuel burns, let me get my different color, as the fuel burns away, it'll also burn away the brake wire. It'll continue to burn, it'll burn away the next one, and so on. And the time between the burning of these wires is actually the exact regression rate, well, not the regression rate, but the burn rate of the fuel at that point. But we're going to need some electronics to hook up to these brake wires and to measure the actual speed. We're also going to measure the thrust that comes out of the motor as the gases escape. We're going to put a load cell under the motor, which is basically sort of a beam arrangement that's fixed at one point and that can bend on the other point, and with strain gauges on this load cell you can electrically measure the deflection of the load cell, and so the thrust of the motor as well. We're also going to put a pressure tap with a piece of tube for a pressure transducer on it. So basically we'll be able to measure the pressure, the thrust of the motor, and also the burn rate of the fuel of the motor. Now, to test these properties of a static motor test, we've developed a piece of hardware and software running on it, which is this board here, which basically reads in the values from the load cell, the pressure transducer, and the brake wires. And it displays it on screen, so you can graph it, you can process it. Now the really nice thing about this board is it's got a really high sample speed and it's an integrated system. What you would usually do for these kind of tests, for a load cell for example, if you want to measure the thrust of a rocket motor, a load cell is has a bit of an awkward signal coming out of it. It's a really small millivolt differential signal for which you will need an amplifier to amplify it. I've got a small amplifier from Moonlight Electroworks here, which is basically an amplifier that you can hook up to the load cell, and it'll give you a nice clean 0 to for example 5 volt signal, which you can measure with an analog to digital converter or whatever. So typically you would also have an AD converter. This is a very well-known one. It's a Daytag. It's a rather cheap unit, but you can see where this is going. If you're out in the fields, you're doing a static test, you've got a lot of wires dangling, you've got a lot of devices you need to take care of, so it's not really a very convenient testing solution. So this basically is an all-in-one solution. It's got an interface for a load cell with an integrated amplifier, which is the INA 125 by Burr Brown, which is well known in the rocketry community for use with load cells. There's a port on it for a pressure transducer, both the 0 to 5 volt type or the 4 to 20 milliamp industrial pressure transducers. And it's also got a few connectors in which you can plug in shields. It's kind of like Arduino style. There's a bit of a few expansion pins which you can plug shields in, and they'll, for example, give you the interface to hook up brake wires, or it'll have a connector with an SD card, so you can log your data to an SD card, and you don't need to keep this unit plugged into a computer anymore. But that's for the future. Okay, now let me demonstrate a current prototype version of this controller board. So let me just switch the board on. This is a standard terminal session. It comes with any operating system. It's just a regular serial terminal. Let me just connect to the controller board. So when we connect it, it gives a welcome message. Which says what firmware version is running, and it also shows if there's any shields attached. If you plug in shields, it'll auto-detect if there's a shield plugged in when you boot up the system. And then it gives a command prompt. So this is like MS-DOS from, well, a couple of decades back. You can tap a question mark for help. It'll give a help menu, and you can set a number of options within the board. For example, let me set the sample speed. Let me set that to 100 Hertz, and then you can write it to the memory within the chip, so it'll keep it when the power is disconnected. Inside of the board there's a circular buffer running, which is constantly taking a look at the load cell, pressure, transducer, brake wires, and it'll constantly write these measured values inside of a buffer. Once the system detects that one of the values is going up, it means that the test has started, and basically then it starts outputting values to the serial terminal. Now we can simulate this by doing a force start. So I'm going to type an F, and you can see the value scrolling. So it's 100 Hertz, which is 100 samples a second at the moment. The left value is the load cell, the middle value is the pressure transducer, and the third value is a buffer error value, which is basically used for debugging at the moment. So you can see when I'm going to push on the load cell, you can actually see the first value increasing. There's only so much force I can put on this, so I'm not going to go all the way up to the range, but you can see that it's varying. If I go and wiggle around my PSU voltage, you can see that the pressure transducer, the value is going up and down as well. So if you capture this data to a text file and you import it in a spreadsheet like Excel, it's very easy to graph the different properties of the motor test that you're currently doing. So that's going to be a really neat system. So this system isn't finished yet, but let me just show you another neat thing about it. This is a prototype of a brake wire shield. It's got a connector for brake wires, and it's got a couple of LEDs which show what is connected and what is not connected. So let me just put this on. This is a really crude version. Let me just disconnect the pressure transducer first. The board is now powered off. If you plug it in when the board is powered on, then you're going to have a problem. Okay, let me just see if this fits now. Okay, that should do the trick. So I'm going to plug it, I'm going to switch it on now. I've put power on the system. Let me reconnect. So there's my command prompt, and you can see that it now has detected the brake wire shield. So now with the B command I can check the brake wire status. So here it's 0000. I've got a pin header here which is shorted across the pins to signify a brake wire. So if I plug that one in, you can see that the LEDs are going on, and if I do a B, now you can see 111. If I wiggle it around a bit, let me see if I can do that. So let me keep B pressed, and you can see that the values are changing as the brake wires are changing. So that's going to be a really handy way to see if any brake wires break or reconnect or whatever. So there you have it. That's what I'm currently working on, the static test controller. Basically no more need for amplifiers and AD converters, DATACs, whatever. It's an integrated system which you can easily take into the field and do your static test. Thanks for watching.